In a high-traffic distributed system, the persistent SQL database is often the weakest link. When millions of concurrent read requests hit the central storage layer at once, disks spin, queries queue up, the entire system slows to a crawl. To protect that database, engineers deploy a volatile, in-memory caching layer. Memcached sits directly in front of the database, intercepting these read requests and serving them from RAM before they ever reach the disk. Memcached is designed around a singular operational metric, speed. It reads, writes, and deletes key value pairs with O of 1 constant time performance, guaranteeing data retrieval in under a single millisecond. Retrieving a single string from RAM in under a millisecond is trivial. Doing it simultaneously for tens of millions of concurrent operations, while network nodes fail and data expires, requires highly specialized engineering. To understand how Memcached operates under enterprise loads, we have to look inside its execution core. We'll examine its multi-threaded concurrency model, its segmented LRU memory allocator, and algorithms preventing catastrophic traffic spikes. By stripping away standard database features, Memcached uses architectural minimalism to process billions of requests per second. The foundation of Memcached throughput is its master worker threading model, built directly on top of the asynchronous libevent library. At the entry point of the server, a single dedicated dispatcher thread listens on the main TCP socket. When a client connects, the dispatcher accepts the socket and hands it off to one of several active worker threads using a round-robin distribution. To process data across all these grids simultaneously, Memcached utilizes multi-granular item locking. Instead of freezing the entire cache for a single write, it hashes keys to a specific table of mutexes. This allows multiple CPU cores to read and write different items at the exact same time without data corruption. Compare this structural approach to early versions of Redis. Historically, Redis operates on a single-threaded execution loop, processing incoming commands sequentially, one item at a time. Redis accepts this single-threaded bottleneck because it supports rich data structures like lists and sets, handles large payloads up to 512 megabytes, and writes data to disk for permanent storage. Memcached drops all of those features. It operates entirely in volatile memory, restricts keys to just 250 bytes, and hard caps values at 1 megabyte. By sacrificing data structure variety and disk persistence, Memcached natively saturates multi-core processors. You simply add more cores to handle more concurrent operations, keeping the deployment structurally flat and operationally light. Stepping out of the CPU and into the physical server rack, engineers face the problem of how to distribute the required RAM across a fleet of servers. One approach is the web server integrated layout. If you have dozens of web servers with unused capacity, you can dedicate 1 or 2 gigabytes of spare RAM on each machine to run a Memcached instance. This wide dispersion minimizes the blast radius of hardware failure. If one web server dies, you only lose a tiny fraction of your total cache. The cluster's overall hit rate stays high, insulating the database. Alternatively, you can condense that memory into a dedicated layout, deploying just 4 massive, purpose-built servers with 144 gigabytes of RAM each. The physical footprint is smaller, but the failure risk is highly concentrated. If just one of those dedicated nodes loses power, 25% of your cache vanishes instantly. A sudden drop from a 90% hit rate to a 70% hit rate shifts your miss rate from 10% to 30%. In that moment, the raw read volume hitting your backend database exactly triples. Cluster architecture is an exercise in risk management. You distribute physical hardware based strictly on how large of a cache miss spike your database can absorb without failing. Inside the RAM of a single node, Memcached has to manage how data moves and expires. Under heavy read and write workloads, high-churn data can cause severe memory fragmentation and lock up the system. Early versions of Memcached used a single, unified, least recently used, or LRU queue. Every time a client accessed an item, the system had to lock the entire queue just to bump that item to the top. Across millions of reads, CPU cores ended up idling as they waited for these queue locks to clear. Modern Memcached solves this with a segmented LRU architecture. Memory is divided into 4 distinct subqueues, each protected by its own independent lock. The first is the temp queue. It isolates transient items with ultra-short lifespans. Items here are strictly exempt from being bumped when read, entirely bypassing CPU lock contention. Newly written items with standard lifespans enter the hot queue. This acts as a probationary area. Crucially, items in the hot queue are never bumped when accessed. This intentional friction eliminates write contention when a new key suddenly experiences a massive spike in reads. If an item survives the hot queue and is accessed multiple times, the system promotes it to the warm queue. This acts as a safe haven for items that demonstrate sustained utility to the application. Finally, items that sit idle fall to the bottom of the hierarchy, the cold queue. This serves as the eviction pool, where unaccessed items wait to have their memory reclaimed. Moving data between these segments is handled by specialized background threads, the LRU maintainer and the LRU crawler. The crawler asynchronously scans the cold queue, looking for expired items. It reaps the stead memory in the background, freeing up space without ever pausing the active worker threads serving clients. By isolating lock contention and managing evictions asynchronously, the segmented LRU prevents the cache from choking on its own metadata. The node's read and write throughput can scale linearly alongside the hardware. Even with perfectly optimized memory allocation, caching systems face catastrophic systemic threats. The most dangerous is the cache stampede, also known as the thundering herd. A stampede triggers when a highly popular cache key reaches its exact expiration timestamp while thousands of concurrent users are actively requesting it. In a fraction of a millisecond, thousands of read requests hit the cache, discover the key is missing, and simultaneously bypass Memcached. They strike the underlying database all at once, causing an immediate congestion collapse. This diagram illustrates the read and write paths Memcached uses to mitigate this exact scenario through its first line of defense, lease-based locking. When that initial cache miss occurs, Memcached issues a unique 64-bit lease token. Crucially, it only gives this token to the very first client that experiences the miss. All concurrent clients requesting that exact same key are denied a lease. They are instructed to wait or are served slightly stale data. This mechanical throttling completely shields the database from redundant queries while the first client performs the single necessary read. The second defense attacks the root cause before the key even expires, using probabilistic early expiration. This equation dictates how worker threads evaluate items approaching the end of their time to live. Instead of waiting for the exact expiration timestamp, the system makes an independent, calculated decision to recompute the value early. As the expiration window tightens, the probability of an early recomputation scales upward. Because this decision is randomized across independent threads, client recomputations naturally stagger themselves, dispersing the herd before it can ever form. At enterprise scale, Memcached serves as a protective throttle, strictly regulating how failures and expiration events cascade into the storage layer. Memcached remains an industry standard because its constraints are its features. By refusing to support disk persistence or complex data structures, the codebase is entirely devoted to raw, multi-threaded CPU saturation. Its segmented LRU architecture maintains precise memory allocation without stalling worker threads, efficiently processing massive volumes of volatile data. Its lease tokens and probabilistic expiration algorithms form a mathematical shield, absorbing traffic spikes that would otherwise shatter a database. Memcached provides the foundational blueprint for distributed caching because it accepts a harsh truth of systems engineering. Cache expirations and server failures are not rare anomalies. They are the baseline conditions your architecture must be designed to survive.